Welcome to Digital VLSI Design Virtual Lab, experiment number 2, CMOS inverter characteristics. The aim of this experiment is to plot the static and dynamic characteristics of a digital CMOS inverter. In order to begin, click on the Simulator tab. In this new page, 3 links are provided. The first one corresponding to the static characteristics and the next two corresponds to the dynamic characteristics. We will begin looking at the static characteristics of a CMOS inverter using ngSpice. To do that, click on the first link. A new page will appear in which on the top of the page you have the schematic diagram of the circuit setup for plotting the static characteristics of a CMOS inverter. On the left bottom you have the SPICE code, and on the right bottom you have the space for plotting the static characteristics. Let us look at the ngSpice program code for plotting the static characteristic curve. Line 1 corresponds to a DC voltage supply of 1.8 volt applied between node N1 and node 0, and it is labeled as V1 in the first line of the program. Line 2 and 3 corresponds to the definition of a PMOS device, which is labeled as MP, and an NMOS device, which is labeled as MN. The PMOS device, with its drain connected to node 2, gate connected to node N0, source and bulb connected to node N1, are defined in line 2. Similarly, the drain of the NMOS device is connected to node N2, gate is connected to N0, source and bulb are connected to node 0, as shown in the third line of the program. Finally, an input voltage source is applied between node N0 and node 0, and this completes the components in the circuit setup. A .dc analysis command is used to vary the input voltage from 0 to 1.8 volts in steps of 0.1. The following part of the program corresponds to specifying level 49 SPICE model for a PMOS device as well as an NMOS device. The program ends with a .n command and a run command. Now to begin to run the program, click on the Simulate tab. It will take a while for the transfer characteristics to appear on the right bottom of the page. The x-axis of the graph corresponds to the input voltage sweep, and the y-axis corresponds to the output voltage of the inverter. One can evaluate various parameters that corresponds to the performance of a digital CMOS inverter, such as noise margin, from this static characteristic curve. In order to do that, first of all, we need to identify 2 points in this curve where the slope is -1 radians or -45 degree with respect to x-axis, which will come around here and the other here. By following the procedure we have listed in the theory section, one can evaluate the noise margin for the low state as well as the high state. In order to perform the dynamic characteristics of the device, go back to the Simulate tab and click on any of these second links. Link 2B is a magnified version of link 2A, wherein the waveform is magnified in order to see the details of the time domain analysis. Let us look at the dynamic characteristics by clicking on link 2B. In this new page, we have a similar schematic diagram of the circuit setup as we have seen in the case of static characteristics. The only difference being is in the specification of the input voltage source Vin as given in the second line of the SPICE program. This voltage source is applied between node N0 and node 0. The pulse waveform is specified with its low state as 0 volts, high state as 1.8 volts, delay of the pulse is 0, rising time is 1 picosecond, fall time is 1 picosecond, the on period is 0.5 nanosecond, and the full time period of the pulse is 1 nanosecond. Rest of the program code remains the same except for the addition of a transient analysis command at the end of the program, which specifies the sampling period as 1 nanosecond and the simulation time as 2 nanosecond. One also has the provision to specify the start time of the simulation, which here is 0 nanosecond by default. In order to plot the dynamic characteristics, click on the Simulate tab. Two waveforms will appear, one corresponding to the input of the inverter and the other corresponding to the output of the inverter. The input of the inverter is as specified in the SPICE program code, with 0.5 nanosecond as the on time and 1 nanosecond as the total period of the pulse waveform. Notice when the input voltage is at high, the output of the inverter comes as low, and similarly when the input voltage waveform is low, the output of the inverter is 1.8 volts or the high state. It takes the rise time for the output of the inverter to rise from low state to the high state, and similarly it takes a time called as the fall time for the output voltage to switch from high state to low state. We can measure this rise time and fall time by appropriately magnifying the output characteristic curve at proper instance. For example, in order to measure the rise time, let us magnify the output waveform for a time between 0.4 nanosecond to 0.6 nanosecond. This can be done by modifying the trans command as follows. Notice the first parameter in the trans command corresponds to the sampling rate, and the second one corresponds to the end time of the simulation, which we modify as 0.6 nanosecond. We need to now give the start time of the simulation as 0.4 nanoseconds. Now let us run the simulation with this new input parameters for the transient analysis by clicking on the Simulate tab. Notice the input and the output characteristic curve is now plotted between 400 picosecond to 600 picoseconds as we required. This will help us to measure the time more clearly for the output of the inverter to rise from low state to the high state. Thus, we can evaluate the rise time of the inverter. Similarly, one can also evaluate the fall time by properly magnifying the instance in which the falling edge appear at the output. One can also redo this experiment after modifying the length and the width of PMOS as well as NMOS device that constitutes the inverter. This will help us to study how the rise time and the fall time vary with the design parameters. Thank you.